Hi everyone, in this video we'll discuss the concept of vulnerability measurements. This concept is essential because when you have, there's so many things that can go wrong in your system. You have to have a way to rank them somehow and address the highest priority ones. And to understand priorities, you have to have a mechanism for understanding the severity of vulnerability. So this is exactly what a measurement, a quantifiable measurement, can give you. So we're using vulnerability measurements to ensure that for every weakness, we have a number that allow us to prioritize weakness finding, and whenever we want to take action, we start from the top, the most important weaknesses. And it should be clear by now that some weaknesses can cause more impact than others. It's different that we have a weakness that it has minimal impact. For example, it can only affect a very small part of your system or your network, and an impact that can allow the attacker to gain access to your SCADA system. So in this way, by first of all ranking and then comparing, also that you only because you have a limited budget, typically you only detect and prioritize remediation for whatever is 7 and above, for example. And in this ranking allows us to proper manage our resources and our efforts towards understanding and fixing weaknesses. To understand vulnerability measurements, we need to understand 3 different concepts: CWE, CVE, and CVSS. I'll give a brief introduction here, and then we'll go into describe each one of them individually. CWE stands for Common Weakness Enumeration and has to do with the vulnerability type. This is not the instance, but just the type, a generic type. For example, CWE 261 stands for Weak Cryptography for Passwords. The way you're storing or you're creating or you're enforcing your passwords, you have a problem with your cryptographic scheme or the way you have implemented cryptography. So as a type of vulnerability, the title is Weak Cryptography for Passwords. Then CVE would be an instantiation of this vulnerability in a specific product. So you have the product from vendor X, and within the firmware of this product, there's the instantiation of that specific type of vulnerability, the weakness of weak cryptography, and this will belong to you create a CVE that will mention that this specific product, for example, a relay, has this type of weakness. The way the relay is storing the password is weak and you need to fix it. But so this is an instance, and the CV typically is broken down to the year it was created, and then it has a numeric ID associated with it. So CV 2017-7905 would be that a specific product of the vendor has this weakness. And then to prioritize the weaknesses, you need a scoring mechanism, and that's exactly what CVSS is. CVSS stands for Common Vulnerability Scoring System and gives you a number from 0 to 10, measuring the severity of the vulnerability. So, for example, for this product that has this weakness, that CV, we can report a CVS score, let's say, of 8.1. And since this goes from 0 to 10, you can rank what are the most important vulnerabilities in your system. Let's see each one of these metrics individually. CWE, we discussed, stands for Common Weakness Enumeration, and it's a community-developed list of software and hardware weakness types. In a way, it serves as a common language. So when I say buffer overflow, someone else can understand exactly what I mean. Same with cryptography or out-of-bounds write or other things that are common between different software and hardware implementations. As of March 2020, the CWE list contains more than 900 entries, and it's split in 3 types: software, hardware, and research concepts. CWE is very useful for various reasons. One, as I just said, you can have a common language that you can describe software and hardware weaknesses. So when you describe a weakness cross-site scripting, the other side understands exactly what the problem is with your software. You can use a list to go over it and check for those weaknesses in your software and hardware products. So if you have 900 entries, you can possibly go through all of them and understand whether your product is specifically affected by each one of these weakness type. You can see whether the tools you have selected for security assessment are targeting these weaknesses, and you can fully understand whether you have exhaustive coverage of your security mechanisms. And then you can use this CWE to have a common baseline standard for identification, mitigation, and prevention. So even if you are talking to different vendors or different security companies, you can speak the same language, CWE, and you can tell them, are you covering all the possible weaknesses that can exist in my software and my hardware? And finally, of course, you can use that list to make sure that your software and hardware is free of vulnerabilities prior to actually deploying them. This is published by Mitre. This is the top 25 CWE for 2020. Again, CWE is a type of vulnerability, not specific instances. But this scoring is a combination of both how the severity of vulnerability and how often they appear in the wild. And you see the top CWE would be the cross-site scripting attack that you may be familiar with, followed by out-of-bounds write, improper input validation, out-of-bounds read, and then problem with bounds of a memory buffer, like buffer overflow attack. So these are the top CWEs that appear in software and hardware for 2020. And you can go to the website of Mitre and look at the list of weaknesses yourself. Every year, the top 25, of course, are expected to change. You can see all weakness type by going through at the site. You can look at the top 25. This is what we just saw. But you can browse through them, all the 900 ones separately. You can see them on the software view, all these different types of things that can go wrong, from cryptographic issues to file handling issues, memory buffer errors. These are categories that you can further expand and see specific types. And so here we have our classic buffer overflow, which is a very common vulnerability that can be exploited for remote code execution. So you can see more details about that weakness type, what the description of it, and then relationships, what other relevant concepts exist, use after free, improper null termination. There's some kind of hierarchy developed by these CWE categories. All right, so that's for CWE. Then we have the CVEs. CVE stands for Common Vulnerabilities and Exposures, and they are vulnerabilities in a specific product. Every year we'll have more and more of the CVEs as we understand and we explore and we try to test the systems, both software and hardware. We may find vulnerabilities, and when we find something, we report it, it gets a CVE assigned, so everyone else who has the product knows that this product has a specific vulnerability, and that will be the CVE. So it's another glossary, and it's a project dedicated to understanding all vulnerabilities that exist in software and hardware. It's also maintained by Mitre with funding from the Division of Homeland Security of the United States. Examples of CVEs here have CVE 2020-7569. It will have its own type, as we discussed before. That will be CWE434. Stands for unrestricted upload of file with dangerous type. This affects a unique instance of a product. That will be the EcoStruxure in this example. EcoStruxure building operational web reports, specific versions of it, because after that probably a patch exists that remediates the vulnerability, fixes it. And a short description says that because of this weakness, an adversary is able to upload arbitrary files due to incorrect verification of those files, and at the end, the adversary can achieve remote code execution. Another CVE 2017-2680, that's more related to ICS. You can send specific Profinet packets, and these packets can call a denial of service condition because of the parser of the software parsing the packets is not properly validating some things, some bounds checks, and because of that, you may have the system hanging, and that leads to a denial of service attack. You can go to the website and see all the CVEs. There are many of them you see as of today. More than 150,000 exist, and you can browse through them because there are too many. You can search by keywords, by IDs. Let me just try to find, for example, Siemens. So you see, by typing Siemens, I find 267 records for all the Siemens products. And if you click on each one of them, they're ranked by year of release. And the latest one, that will be this one, that details the specific product affected and how it's affected. Again, see, cross-site scripting is one of the weakness type, and we saw that weakness type before as the major one for 2020. So if you have this specific Siemens product, the Spectrum Power, you have to take action for fixing that vulnerability, and typically the action would be applying a patch. But before the patch can be applied, you can do other things to ensure that the vulnerability cannot be exploited by the adversary before the patch is applied. So that's for CVE. And again, every CVE would need to have a weakness metric. How bad is the situation? How bad is the problem? How important is the weakness? And that's exactly what the CVSS does. CVSS is a common vulnerability scoring system, and it's just a number from 0 to 10. And this number is reflecting the severity of the vulnerability. So the closer to 10, the more severe the vulnerability is. The closer to 0, the less severe is, and you may choose to ignore it. But if something is closer to 10, you should probably take action for this vulnerability. It's very important to note that CVSS is not about risk, but it's about severity. So the risk is dependent on other things, for example, likelihood of attack or window of opportunity or your specific threat modeling, your threat actors. So CVSS is how severe the vulnerability can be, but not your risk. In the following lectures, we'll discuss risk management and risk assessment. Here, you get a numerical score, and then assuming other things, you can have a qualitative representation, low, medium, high, critical, to further help you with your vulnerability process. Because CVSS score may be 10, but for example, the likelihood of this happening could be very low. So your risk can be ranked as, for example, medium. And then you have a CVSS that's scored, for example, 8, but the likelihood of this happening is very high. So that would be a higher risk compared to the previous one that has higher CVSS but low likelihood of occurring. CVSS has 3 components, and the first one is the base score, and that is the intrinsic qualities of the vulnerability. It's important to split between base, temporal, and environmental because the severity of vulnerability changes over time and within the unique environment. So base is constant, is the base score constant over time and across environment, but then we need to also capture the temporal aspect of vulnerability because it's different when a patch exists and a patch doesn't exist, for example. So maybe something is a 0-day, today I have it, I cannot fix it because a patch doesn't exist. So that's higher in a way, this is more important compared to a vulnerability that has the same base score, but a patch exists. So I need to have a way to rank my weaknesses also based on the vulnerabilities characteristics that change over time. And also it's very important to also include the characteristics that are unique to my environment. For example, a vulnerability may be a network one, but for me, I never connect this device to the network. So the vulnerability is not as important to me compared to another utility, another company, that they connect the same device to the network so they can be affected by the vulnerability in a different way. So let's see a real example of scoring a vulnerability, of using the CVSS system to produce a number to understand the importance of the vulnerability. So let me repeat one of the vulnerabilities that NYU has discovered in the past on a specific G relay allowed the attacker to take over the device using 3 steps. One, you send a query through Modbus, and that Modbus query would give you back the encrypted passcode. And then once you have, and this happens without authentication, so anyone can ask that Modbus query and then receive the passcode back. Step 2, you reverse engineer the passcode because the algorithm used for encryption was a homebrew one, not one of the standards. So it was possible to, through some cryptanalysis, to reverse engineer the passcode. And then after you have the passcode, you can now authenticate to the system, and you're now in admin mode, so you can change all device set points. By changing the set point, for example, in the power grid, you can cause the breaker to trip in a different voltage, maybe the regular voltage that it senses. So you change the overcurrent over voltage protection thresholds, and this way can cause a denial of service attack to the system. So let's try to rank, to create a score for this vulnerability. So I go to the website, and you see I have the 3 different types here: base score, temporal, and environmental. The base score is fixed, as we discussed before, it's going to be the same. And then after we have the base score, we'll see the temporal score of the vulnerability, because if a patch exists, for example, it's not as important anymore. And then we'll see the environmental one, because it's unique to my environment. When I assess it, I want to understand how problematic this is in my environment. And if I never connect this device to the network, then I'm not as affected compared to someone who has this G device connected to some network. So to create the base scores, I have to fill in all these metrics here. There are actually 2 exploitability and impact metrics. Exploitability starts with the attack vector, and if you hover the mouse cursor over the text, you can see explanation for each one of these metrics. So this attack vector is the context of how to exploit the vulnerability. Can you do it through the network, or can you have to have physical access? And it should be very clear that network will be more severe compared to physical access, because physical access you have to physically infiltrate the plant or the building, the substation, to get access to the device, and that will be much harder attack compared to network access. Because this attack takes place over Modbus, it is a network. It can be exploited through the network. Complexity is pretty low. You just need to ask a Modbus query to start with, right? So it's very easy. You don't rely on very specific conditions that you're in maintenance mode, and you have a specific firmware and specific version, a specific version of Windows at the same time. So it's not really, you just need to ask a Modbus query. So in that regard, the complexity of the attack is low. And then privilege required. Do you need to be an admin or something else? Do you need to have escalated privileges? The answer is no. Anyone with access to the network can ask for the Modbus, can ask the Modbus query to receive the encrypted passcode out. So no privileges are required. Do you need the user to do something? The answer is again no. Remember, we discussed in the Ukraine Power Grid, you had to have the user clicking on enable macros. So it needed some interaction, so it increased the difficulty of the attack. In this case, no interaction was needed. Scope. So what you need to also capture with the severity metric is whether, if you affect this device, this will lead you to affect other things as well. Is the scope of the attack changing after this device is affected? Here, the scope doesn't change, actually. You take over this device and you're staying in the device. You cannot use the device to take over other parts of the system. So the scope remains unchanged. And then on the impact side, you have confidentiality, integrity, availability that become a bit more subjective metrics. I would say confidentiality is probably affected because you can read everything from the device, so you can extract all the information from the device. Integrity is, of course, severely affected because you can change the components, you can change the parameters of the device. And availability, of course, is very high because you can disable the device. So the moment I complete the metrics, you see the bars going up. So it calculated the scores, and I come up with the overall score of 9.8. So this is very serious. This is 9.8 out of 10. That's a very important vulnerability, and probably have to have some mitigation for it. But then I have to also explore temporal and environmental, because this should change over time. If a patch exists, then the vulnerability is not as severe. So moving on, temporal score metrics. There are three things: code maturity. Does this code, the code of exploitation, does it exist? Do we know it exists, or is it just speculation? And then remediation level, is there a patch, does a patch exist or not? And confidence in the report, are these rumors, or do we have from official sources confirmation that this is that exists? Starting with maturity, in the case of the exploitation we're discussing today, there is a proof of concept code. So NYU reported that code directly to Z, so we know that actually, probably we can say it's high maturity, because we know exactly how to deliver the vulnerability. Remediation level, as of today, actually, after we reported that to Z released a patch that fixes that vulnerability. So an official fix exists for that. You don't have to do any temporary or workarounds. You have an official fix from Z. That's exactly why we need the temporal thing. Report confidence, it has been confirmed by Z that the vulnerability exists, and also that the patch exists for the vulnerability. So you see here, we have some reduction in the score. From 9.8, we went to 9.4 because a patch exists for this. So it's not as bad as before, but still is a very important thing to prioritize when we do our risk assessment and risk management. And finally, the environmental score metrics. It kind of repeats the base one, but in the context of my unique environment. For example, here, my attack vector, right? Maybe this is the modified attack vector. Maybe, the device, the vulnerability needs network access, but I don't connect to the network. For you to deliver the attack, you need to have physical access, or you need to, for example, be only in the local network, in the LAN that connects the device to another device within the same network. So let's say physical, for example. It's not connected to the internet, you have to go there in the building. Complexity remains low because it's very easy to do the attack. You don't need any privileges, as you gain privileges through the attack. No user interaction is needed. This hasn't changed in my environment. Scope, same. Scope doesn't change if I take over this device. Confidentiality impact, they're the same, because even in my environment, I have my unique set points. The attacker can see my set points, they can change the set points, and they affect my availability a lot. So this is the modified metrics are actually the same as before, but maybe I don't have really confidentiality requirement, right? If someone sees my set points, I don't care, because these are the expected set points, right? Everybody's using the same. They're established from the control experts that these are the ones you should be checking for overcurrent, over voltage conditions. So my confidence, I don't care much, but I do care a lot about integrity and availability. So I'm putting all these things, and I have a new number here, right? I have a modified environmental score of 6.5 and 5.9, and it's clear this is happening because of the network change. Since I don't connect to the network, the vulnerability importance reduces a lot, and I have something that's much less. I have 6.5 compared to the original 9.8, unique to my environment and for the current time, that also is affected by the temporal. So to summarize, I first do the base score, and then depending on the temporal properties, is there a patch, for example, available, this will change, and then the environmental ones also will further change it to come up with the overall one that in my case for that specific vulnerability as of today is 6.5. And if you're interested, you can click on the SOA equations part, and you can see exactly how the scores are created from all the selections we made in the individual metrics. So going back, the last thing I'd like to discuss is the presence of advisories. And in this example, I discuss the advisories coming from ICS CERT. So we discuss CVEs that are affecting a product, but sometimes a product is being affected by multiple CVEs. So it's good for the company to know all the CVEs that affect the specific product. For example, in this ICA cert advisory, they discuss the specific Simatics S7 Siemens PLC, where they have 3 CVs. One would be with this CWE type, a loop with unreasonable exit condition, creating a DOS attack. So if you send a specific, a specially crafted file, you have the system crashes and you have to restart it. That CV has been assigned, and then the severity of the attack is 5.5. And then for the same product, you have another CV that exploits, that is an instantiation of a different weakness enumeration type. That's the null point dereference. The severity is 5.5 for this, and then you have a divide by 0 CWE with a different CV and a different base, same actually base score 5.5. So the advisories are great because you can focus on the product and find all the CVs for that product, for that version, and try to find mitigation solutions for each one of these CVs.